So unfortunately, I can't see my notes, so I'm going to wing this to the best of my ability. But we're okay. Okay. So the challenge. So current state of the art, speed, scale, fragmented workflows, and reliability is the key roadblock, in our opinion, to why additive manufacturing can't be taken from its current state of prototyping to where it ought to be, which is in a fully blown manufacturing setting. So this is our key mission statement on how we can reimagine additive manufacturing to solve those key issues. So Medusa itself is not just another 3D printer. So we obviously have the large build volume, and we've also integrated the CNC finishing. And that one-click workflow, I'll go into that a little bit more in a minute, is transformational. And the industry reliability gap is what we've tried to solve. And that's from our sort of ground-up methodology on how we've designed the machine. So speed. So when it comes to 3D printing, the sort of misconception is it's slow and it's unreliable and all these sort of things. So the way we thought about this machine, it goes back to that workflow piece. So why do we just print with one tool, or why do we have just one process at the moment? I know there's smaller versions of this where it's an odyssey, but what we've tried to achieve here is actually put these into a full-blown workflow which is fit for industry. So those movement speeds, so we've managed to achieve speeds of 1.2 meters per second, which is quite phenomenal with the weight of that payload. As you can imagine, it was an engineering challenge to ensure that happens. And then the deposition rate as well also makes speed. So when we think speed, so filament speed of the motion system is very important, but for pellet, it's all about speed of deposition. So 17 kilograms per hour is how much material we can deposit. And what that means for industries, for example, the mold tool sector, instead of taking weeks to make a mold tool using various workflows, various suppliers, it means that we can now make a mold in the matter of hours, and we can do that with the minimal amount of interaction as possible using that sort of one-click methodology, which I think is key for mass adoption. So, like I said, the machine has multiple tools, which enables a seamless switching process. Eliminates transfer errors if you're going to be CNCing, because we can, with some of these workflows that are possible with some of the slicers out there, it means that we can now print and mill in the same place. So it reduces labor costs for the manpower not required to move things around, and its cutting lead times, our estimate is circa 16%. So that strategic process, let's go into that in a little bit more detail. So imagine now we have a part which some bits are really intricate, some bits are really sort of big and bulky and linear, and other bits require absolute precision. So the only way you could achieve that before would probably be to just mill a piece of billet. But with this machine, what we are able to do is we're able to, for example, say we have a small part at the bottom with intricate holes with complex curvature. We can pick up our filament tool, and that filament tool itself is no slog in itself. Deposition rate of the filament tool is 0.9 kilograms per hour, which is quite substantial. And that, coupled with the movement speed of 1.2 meters per second, is extremely fast. We've been printing on our filament tool now only for a few days, because it was one of the last things that we managed to put together. But we're already surpassing the speeds of what people in the room think is fast at the moment, which is the Bamboo Labs. But we're doing that in a massive build volume, which is no mean feat. So let's imagine now we've started our filament print, and now we have a piece of ductwork or something which is very high and tall. So we can seamlessly, without any user interaction, the machine will then pick up the pellet tool. It knows exactly where it is in relation to the part that's already been printing. It can now print the tubular part with the pellet tool extremely fast, up to 17 kilograms per hour. And then we can then switch to our CNC tool and finish any side surfaces or top surfaces to ensure that we get precision that's required. And then, so that workflow is completely revolutionary, I think, and it's going to unlock some huge potentials. So why do we say this is built for industry? So many of our competitors have taken up a different philosophy than us. So a lot of them have gone for very lightweight tooling, lightweight chassis. We've gone the other way around. And the reason why we've had to do that is because if you try to throw around a 22 kilogram payload at 1,200 millimeters per second, things tend to move. So our chassis is built like a literal tank. And it looks quite elegant with the way that we've clad and finished it, but under there is a huge piece of engineering work to ensure that it all stays still. And then that, coupled with our comprehensive thermal visualization, means that what we're doing now is we don't just have a big robust machine, we have a big robust machine which is intelligent. And we've been very front heavy on the way that we've integrated sensors. And what we've done that for is ensure that over the coming sort of 12 to 18 months, we can now build out our software capabilities with strategic partners and in-house capabilities to ensure that this machine will get more and more intelligent the longer you have it. And also it is fit for purpose because the extruders themselves will go up to 400 degrees. And with the with all these things coupled together, it enables us to get predictable results. So UI is reimagined. So a UI is it's very close to my heart because I get very frustrated when I click on most pieces of equipment out there. So having a process where instead of 5 buttons you should just have one is our methodology. If it needs to be done in more than sort of 2 steps, generally we have to have a conversation as a team to how we're going to automate that process. And what that's enabled us to do is transition to a sort of one-click workflow. So what does that do for the user? The main thing is it reduces operator decision points. That means this machine is going to be extremely easy for you to train yourself on. And that's extremely important for adoption. So we've worked extremely hard to make the process as seamless as possible. And the logic that we put into the machine ensures that we can go from A to B, and it's a guided path. So the users can't make an error and smash a CNC tool into the bed or whatever it may be, because the system knows exactly what it's doing and where it's going, and that operation won't occur because it knows that it's not in a fixed state to do that. And that's all around the automated parameters and optimization the team have been working on over the last 6 months. So reducing overheads and operational costs, which is very pertinent for the current state of where the world is at the moment. And just going back to that UI and the functionality of the machine, it's what we've really set out to do is to ensure that we have consumer grade usability, but in a commercial, industrial facade essentially. And again, to sort of cut them training requirements, and that system is a one integrated system. So instead of you having to do a capex on say 3 machines, you can now have one machine which achieves the same thing in a unified workflow, which I think is extremely important to make sure that we can streamline everything we're doing. And then that unified workflow isn't just contained to the machine itself. This unified workflow is imagined within the whole factory setting. So the automatic bed removal, of which you've seen on the short video there, is very key in our opinion to making this machine sit in a factory setting. And it's just the 3D printer in the corner. It integrates deeply, and that's at multiple levels. So it's not just the machine itself just sat on its own, and we can send a bed to wherever you want to be, whether that be picking and packing, whether it would be a different post-processing stage, or whether that would be we're just going to put it in to a QA quarantine area. So that can be automated and integrated into your factory setting, but it also means that we can now have multiples of these machines, and we can have a number of our KUKA autonomous robots, and this whole process could be working hands-off 24 hours a day. You could be feeding the machine with a 2-3 ton bag of pellet, and you could say you need 10 of these to be printed, and those beds just come out and get replaced by a new one, which is in the parking rack, and it will just continuously keep printing with zero hands-on. And the way that we imagine us to be able to do that over the coming months is by integrating predictive maintenance into our machine backend. So, for example, every motor knows how many revolutions it's had. And it knows that with those speeds and that amount of time, it means it needs to predictive maintenance instead of like, oh no, it's broken, and we're no longer operating. And then that also feeds back into the modularity of this machine. So the machine itself is based upon a modular principle. So if a high wear part has been installed on that machine, what we've done is we've ensured that it can be taken and changed within a minimum amount of time. So let's put that in perspective. You see the machine on the screen earlier. So you've got the main print module, and you have the two side modules. So the left module is the pellet module, and the right module is filament and controls. So those two modules, sorry, they can be removed by 4 bolts and 4 industrial connectors. So we can essentially take and do a brain transplant on the machine in circa 45 minutes. So if you're a high value customer who cannot have downtime, you could have a full control module sat on your factory floor, ready just in case there was an incident, and then that can be swapped out and refurbished. And then that also brings us on to, it's this slide. It's this slide. Future-proofing and the design. So with our modularity mindset, and it's a deep mindset within the whole company, the whole range is modular. And what that means is that all our components can be upgraded independently. So you no longer spend X amount of hundreds of thousands of pounds on a machine for the manufacturer to come to you and say, oh, would you like to buy our new one next week? That's not how we feel that business should be done. So the way that we would like to change that mindset is the fact that if we upgrade something, you will get that upgrade as an option. And that can be unplugged and plugged back in. And these upgrades will be designed in a sympathetic way. And hopefully it's so easy that a user can do it. And if not, one of our engineers will come down and change those bits out. And that also means that when we look at the innovation, obviously our business is built on innovation, and it's built on the fact that there's always an improvement to be made. So if we design and build a new tool, that tool will be offered out to our clients, and they are able to put that tool on the machine. They don't need to buy a new machine, they just buy a new tool, and they get that additional functionality, which reduces obsolescence. And also, it improves the sustainability, because no one wants to be spending all that money and all those resources on a machine for it to be then chucked away. So a system that learns. So this is harking back to my statement where I said we've really been front heavy on the controls and all the sensors. So we believe that AI is going to play a pivotal part into where the business is going of additive manufacturing, and kind of like where the world's going at the moment. So all these sensors and all that data is going to be utilized in the coming months to improve every time we have an update, that'll be again rolled out. So AI Builder are going to go through some points a little bit later on, one of their keynotes about kind of the bits that we were working on in terms of thermals. But yeah, you'll see, and also the thermal imaging is working next door. So when we open the shutters in a bit and you have a bit of a mooch around, you'll see all that. So just a little bit about the specs now. So as you know, we've got multi-tool, high temperature bed. So the bed will go up to 120 degrees. Heated build chamber as well. Tools will go up to 400 degrees. And also in terms of speed, like I said, 1.2 meters per second, and acceleration is 10 meters squared. So for the complete suite then, so Jewell filament up to 0.9 kilograms, Pellet 17 kilograms, a spindle as a 3 kilowatt spindle, automated tool changing, and integrated quality monitoring. So we have a full vision system which will be integrating AI-enabled defect detection, which plays a role in that 24-hour factory setting that we were talking about there. So for example, if you've set 10 prints off, which is going to take 5 days, and in day 2 it sees there's a problem, and the system can make an informed decision to stop, and that saves on material costs, it saves on time, and then the user gets to improve on the next time. And this is where also our the future and utilizing AI is going to come into effect. It's taking all the data of why it went wrong and how we can improve that for the next G-code slice. So the built-in quality assurance for our high-value customers, mainly the aerospace and the such like, the ensuring that we have a consistency and we have data, I think is the key word there. So the data is extremely important. So when we do a automatic bead calibration, for example, those changes are noted in the machine. So the G code is, I'll explain actually what that sort of automated calibration does. So essentially we analyze the G code, we understand what the average layer height is and the average layer width. The system will then print a bead, thinking that it's printing the right size. And as you know, or you may not know, in between, especially pellet, for example, even a slight change in humidity, or especially a change in material itself, will make a huge impact on how much material is extruded from the extruder. So being able to then calibrate that without any hands-on process, I feel is very key. To make the system more automated, and 2, to make sure that the user, if you notice, I'm trying to take the user out of a lot of these activities, because the user is generally where the error is, unfortunately. So we want the machine to do all the hard lifting. So what would happen is it will scan the bead, and then what will happen is the G code will be manipulated and changed, and it will change all the E values to match exactly what's extruded. So it extrudes, and it senses that actually you wanted a 6mm bead, but I've got a 7mm bead. It will then change the E values to match what it should be as a 6mm bead, and then it will start the print, which means you get the perfect layer every single time. And the reason why you get the perfect layer is, 1, we've got the right flow rate. 2, we know exactly what our tool offset is because we have the mesh leveling. And in terms of 3D printing, the key steps definitely for SDN is a good first layer and good extrusion rate and good cooling, which is managed by our thermal cameras, and you bloody nailed it. So we can do all those things, we're in a really good state. Yeah, okay. So the design environment, so like I said, capable to work with our KUKA autonomous robot, automated material handling. So the machine itself, the pellet module, it has a small pellet dryer inside the machine, which means that we can actually drip feed raw wet pellet into the top. So by the time it gets to the bottom, it's dry, and it's at the optimal level for the pellet extruder to actually extrude. So what does that mean for the factory setting? It means you can have a humongous silo of material, and these long print processes, again, require less human interaction. And then the environmentals, so it has a full HVAC system inside, so we're filtering out particulates and all the other good stuff that you don't want to be breathing in from the additive manufacturing process. And we also have an industrial safety system. So there's a safety PLC inside, so that means you can actually connect it to your factory. It's not just a siloed piece of equipment, it's integrated into your full workflow. And so it doesn't just have an e-stop. It's like one of my pet hates reading spec sheets. It's industrial, it's got an e-stop. That's incorrect. So I think we're going to sum up now. So what does this mean? So it means that we can turn around tooling and other large prints in a fast, efficient manner. We're simplifying the workflow, fewer operations, which means easier and faster training, which reduces operational costs. We have an extended lifespan on the machine, and we're reducing capital expenditure. So this is a slide a little bit about the team. So our team itself has come across these unique challenges with a different set of eyes. And we've brought together a very talented team from across sectors, looking at sort of industrial inspection through to industrial design, and also our very talented mechatronics engineer who's looking at the details and how we can push the boundaries. And all those three things together with a strong vision has enabled us to produce the machine, which you're all going to have a little look at in a minute. So yeah, the final points, we're having a fully factory in the future integration with what we believe is an unprecedented ROI, and automatic quality assurance, and integrated multi-process manufacturing. And I think over the coming months we'll be able to launch lots of videos to sort of show and showcase what that will look like in reality. Unfortunately, we just ran out of hours, and so we couldn't show that for you guys today. But what we will show you today is we have a pellet tool being printed, a mold tool being printed with our pellet extruder on the machine at the moment. And also we will show you an automatic bed and load using the KUKA autonomous robot a little bit later on in the day. And we'll make an announcement when that is. It's going to be circa 3 o'clock. I think we're running a little bit behind schedule, but that's all good. To work on it. Perfect. So like I said, so demonstrations will be launched on our socials in the sort of coming weeks of some of the bits that we weren't able to show you today. And Jay Can will be talking to you later with the closing remarks and about sort of the future of where we're going, and in terms of the innovation piece that we're striving towards in our roadmap. And then also offer discussions on any early adopters that would like to take a beta machine and understand kind of the good bits, the bad bits, and help us to really make this one of the best additive manufacturing pieces of equipment in the world. That is it. Thank you very much, guys. What do you got?